Let's talk about chiral molecules that have multiple chiral centers within it. A molecule like the one presented here has the following two chiral centers, right? And we did talk about this in a previous video. You simply look for the carbon that has 3 or more connections and you see if it has 4 different groups. The carbon here with 3 connections has 2 methyl groups bound to it, so that does not qualify. But the other 2 carbons here do have 4 different groups bound to it. So technically speaking, this molecule contains 2 chiral centers. So what we need to do is, in terms of naming the molecule, it's find out the longest chain. And the one highlighted in orange is the longest chain uh, for the parent. And counting the number of carbons, we find out this is a total of 9 carbons. So this is a no-name structure. And notice that the substituents, the things sticking out of the parent chain, are methyl groups. We have 3 methyls, therefore this is trimethyl. And we have methyl groups at positions 2, 5, and 7. So this is 2, 5, 7 trimethyl. Nonane. All right, now that's the regular stuff. But what we need to do now is figure out what are the configurations at positions 5 and position 7. Oh, and also, just to make sure that this is the correct name, you want to go the opposite way with the numbering. So if the right end is position 1, that makes the left end position 9, in which case the methyl groups are at positions 3, 5, and 8. All right, so you compare the numbers. 2 becoming 3 is bad. 5 becoming 5, no change. 7 becoming 8 is no good. So you have 2 bads by making those changes. So you want to keep the 2, 5, 7 as your proper numbering scheme. All right, now let's focus on the chiral centers. What we need to do is assign priorities. And in the case where you just have carbon, carbon, and carbon bound to it, the best way to do it is to see, you know, what exactly this is in terms of hydrogen. So for instance, this carbon up here is a CH3. This carbon here is a CH2. And that carbon there is a CH2. The carbons that have the least number of H's by default have to have more carbons bound to it. So the red and the pink segments that are only CH2s are higher priority than the CH3. So this tells us that the CH3 is going to be priority 3. Right? And so you can kind of see that there. So 3 H's versus 2 H's, which means that you have one carbon bound to that center. Okay, so priority 3 is going to be the methyl group up there. Now, these positions that contain 2 H's are equivalent. So we need to move further out into the red chain and further out into the pink chain. And what we see is that the next segment is a CH2 in the red chain. On the pink chain, this is a CH. And what that basically means is that this contains a carbon that has 1 carbon and 2 hydrogens bound to it. This one contains 2 carbons and 1 hydrogen bound to it, right? So looking at that level of hydrogen is the easiest way to go about it, right? CH2 is lower priority than CH. So this tells us that the first priority is the pink segment, the second priority is the red segment, and of course the methyl group was priority 3. And since this carbon has to have 4 things bound to it, priority 4 is the hydrogen that hasn't been written out because it's the bond line formula. So what we do is we simply say, well, the lowest the lowest group is pointing away from us. So whatever happens to the rotation here is indeed the configuration of the molecule. So we go from priority 1 to priority 2 to priority 3. And this shows that the rotation is clockwise. So this is an R configuration at this particular spot. And since this is position 5, this is the 5R configuration. All right, now let's take a look at the second chiral center. We do the same type of analysis. We have CH3, CH2, and CH2. So CH3 is going to be priority 3. Now for these carbons, we have to extend farther out. So we go from CH2 to CH. We go from CH2 to CH3. CH wins over CH3 because you have more carbon content. So the blue segment is priority 1. The pink segment is priority 2. Now here, since the bond is dashed, what this tells us is that the hydrogen that's still bound to this chiral center is going to be pointing towards us. So whatever the rotation is here, the actual rotation is the opposite. So if we go from priority 1 to priority 2 to priority 3, this seems to be the clockwise configuration or R configuration. But because the lowest point is going towards us, the actual configuration is not R, but rather S, right? So that's the easier way to go about it. Okay, so this is position 7, this is 7S. So all we need to really do is in front of the molecule, within parentheses, we write that out, 5R, 7S. And the idea is that you want to go in numerical order. So you want to list the configuration at position 5 first, then the configuration of position 7 is listed, and you separate them by commas. But the entire thing is in parentheses in front of everything else for the name. Okay, so that leads us into the discussion of enantiomers, because before, when we talked about enantiomers, it was simply you have the R enantiomer for one, you have the S enantiomer for the other. But the question now becomes, well, what happens when you have multiple chiral centers? What is the enantiomer? And technically speaking, the definition of enantiomer is that you have to draw the mirror image. And as long as you draw the mirror image, you have the enantiomer of the molecule in hand, potentially. To make this discussion easier, I'm going to make a few abbreviations. The entire pink segment right here is known as isopentyl, so I have the IPN to represent that entire pink segment. And then this thing right here, which is 2 carbons long, is technically an ethyl group. So I'm going to introduce that to make the molecule a little bit smaller. Okay, so as I was saying earlier, the definition is, you got to draw the mirror image of this molecule to find out what the configuration of your enantiomer is. And technically speaking, if ethyl is pointing closer to the mirror, it still has to point closer to the mirror on the mirror image, right? So you have this almost like inversion altogether of the molecule. If you do the analysis of what's happening at the configuration here, you're going to find out that the configuration is S, and the configuration over here, you'll find out it's R. And if you compare it to the original molecule, what ends up happening is that you actually change the configuration of every chiral center. And that's what it means to be an enantiomer in a molecule that has multiple chiral centers. Now, even though drawing the mirror image is the perhaps easier way to go for small molecules that contain only one enantiomer, it is a little bit cumbersome and a little bit confusing to do it with bigger molecules or molecules that have multiple chiral centers. So instead of doing what we just did right here, what I recommend is that you simply redraw the molecule exactly as is. Just draw it exactly as is. And of course, if you do that, the configuration is R and the configuration is S. But now we know that the enantiomer of a molecule with multiple chiral centers is going to have all the chiral centers becoming the opposite. All you have to do is change bold bonds to dash bonds and change all dash bonds to bold bonds. And the moment you do that, this becomes the S configuration up here. Change that dash bond to a bold bond and automatically this becomes the R configuration. And without having to go through the trouble of drawing the mirror image and then having to rotate the whole thing and try to figure out what's what, you are in essence just copying and pasting the molecule and just changing bold bond to dash bond to ball bond, and you got yourself your enantiomer. This is the easiest way to go about drawing your enantiomers. But once again, the key idea is that every chiral center has changed. Every single chiral center has to change in configuration for you to claim that you're dealing with the enantiomer. If you're not, you're going to be dealing with something else. And that something else is going to be the topic of the next video. But I'm going to give you one more example to kind of finalize this idea of looking at enantiomers in molecules with multiple chiral centers. So in this molecule, the main parent chain is the cyclohexane ring. And this cyclohexane has a fluoro group attached to it. So this is the 3-fluorocyclohexane group. The first position is where the cyclopropyl group is located. But notice that the cyclopropyl group has a methyl group attached to it. So technically speaking, you have to write this as a substituent of a substituent. Position 1' is the one that connects to the parent chain. Position 2' is where the methyl group is located. So notice that here in the name, in parentheses, you have 2' methyl, 1' cyclopropyl, letting us know that the attachment is through position number 1. And then you have your 3-fluorocyclohexane. So this is the name of the molecule without looking at the chiral center. So now we're going to investigate what chirality we're dealing with. And we start with the first chiral center right here. And I'm going to go with the simpler method. So let's look at what we have for the groups. This is a CH3. This is a CH2. That's a CH. The lesser H content is automatically the highest priority. So CH is priority 1, CH2 is priority 2, and CH3 is priority 3. Looking at the rotation, we go from 1 to 2 to 3. This looks like an R rotation. So we look at the bond. The bond is dashed. That tells us that the hydrogen, which is priority 4, is actually pointing towards us. So this is not actually an R rotation, it's in fact an S rotation. Okay, moving on to the next chiral center. What's attached to this carbon is CH2, CH, and over here we have another CH. So CH2 is going to be priority 3. For the CHs, we move further out. So this is CH. Next to it, you have a CH2. For this CH, we have also a CH2. If we keep going forward on this thing, we go from CH to CH2 to CH. But over here, we can go from CH to CH2 to CH. But this C also has a fluorine bound to it. And since fluorine is heavier than carbon, automatically the blue segment becomes priority 1. So we have priority 1, priority 2 for the red, and priority 3 down here. So altogether, this looks like it's an S configuration. We are going counterclockwise. But the bold is bond, so that tells us that because the bold is bond, the hydrogen, priority 4, is pointing away from us. So this is indeed the S configuration. And so we got the chiral centers for the primes in the substituent. So we can actually input that into the name of the substituent. And notice that we're putting that inside the big parentheses because it corresponds to the substituent and not the parent molecule. Okay, moving further into the molecule, we have this chiral center over here, which has CH bound to it. It has CH2 and CH2. CH is going to be priority 1. For the CH2 in blue, we move on to this other CH, but that CH has a fluorine bound to it, whereas the pink segment, going from CH2 to CH2, there is no bigger atoms than fluorine. So the blue segment that does contain the fluorine is the second priority, and the pink segment is priority 3. So looking at this thing, it seems to be a clockwise rotation. And since the bold is bond on the chiral center, the hydrogen is also pointing away from you. So this is indeed the R configuration. Moving over to the final chiral center, fluorine is heavier than carbon, so that's priority 1. Then we look at the red segment. This is a CH2. The pink segment is a CH2, so we move further out. This is a CH. On the pink segment, this is a CH2. So CH wins over CH2. Therefore, priority 2 is the red, priority 3 is the pink. And going from 1 to 2 to 3, this looks like it's a counterclockwise rotation, meaning that this is the S configuration. Since the bond is bold, this means that the hydrogen is pointing in the opposite direction from where we're looking. And because of that, the S rotation that we seem to have here is indeed what we have. This is an S configuration. And so now we have everything at hand. at position 1 we have the R configuration, at position 3 we have the S configuration, and since those are part of the parent chain, they go in front of everything else. 1R, S, 1R, 3S, and inside the parentheses we have 1 prime S, 2 prime S. Once again, the assignments are based on increasing order of the numbering scheme. So 1 comes before 3, 1 comes before 2. Okay, so in terms of drawing the enantiomer of this molecule, the easiest thing by default is to copy and paste the molecule as is. And all you want to do is change all the ball bonds to dash bonds, all the dash bonds to ball bonds. And so by doing that, you have automatically changed the 2 prime position from being S to being R, the 1 prime position from S to R, the 1R position to 1S, and the 3S position to 3R. So technically speaking, you have changed every single configuration to the opposite. And the moment that happens, you got yourself your enantiomer. In the next video, I'm going to show you what happens when you have a partial change of the configurations, in which case we're dealing with something known as stereomers. So I'll see you in the next video.